Okay, so we're still in 4.2. The first video we talked about the summation notation. Now we can talk about the area under a curve. And so what types of curves are we talking about? Well, about f of x is the square root of x. Right, so the graph, roughly speaking, looks something like this. Right, basic shape of it. And so what do we mean by the area under the curve? Because obviously underneath it goes on forever. But what we usually mean is the area between the x-axis and the curve, right? So we're stopping down here. This is sort of the lower boundary, and then this is the upper boundary is the curve. And then you might say, well, wait a minute, that area goes on forever as well because the curve goes on forever this way, right? So that's true. So we need to basically say where we're starting and where we're stopping, right? So let's say we start over here, and this looks like x equals 1, but okay, let's call it x equals 1, right? And then we have x equals 2, x equals 3, x equals 4. This is very hard to do here. Pretend this is a straight line. Gosh, right. So this is x equals 4. Right. Now, the region between these two vertical lines and the x-axis and the curve, that's going to be some finite area in here. I can't fill in the whole thing, but you get the idea, right? So we want this area here. We want to calculate that area. Okay. So how to find that area? Right. Well, right. Not easy. Not an easy process, right? So here's the idea. We're going to take this curve underneath here, and I'm going to maybe write it a little bit bigger over here, if I can. Maybe a little bit sloppier, but a lot bigger so we can see what we're trying to do here, right? So here's the curve again. And again, we're starting at 1 and ending at 4. So we want this area in here, right? So yeah, in general, that's a very hard thing to do. But we're gonna start simple. What we're gonna do is approximate it by using areas of things that we know how to calculate areas for. For example, rectangles, right? We know how to find the area of a rectangle, right? It's just length times width, although here I'm going to call this the width, and I'm going to call this the height, because it's vertical. Is that okay? Right. So we know how to find the area of rectangles. So I'm going to divide this region, this red region in here, into rectangles, right? So this will be the first rectangle, and again, this is not going to be exact, but pretty close. This will be the second rectangle. Forgive the sloppiness. This will be the third rectangle. This will be the fourth one, oops. And so on, right? Tedious process, and it is, but it's a good way to get a pretty good answer, or an approximate answer, right? This will not be exact, of course. And I think we can fit one more in here. Yep. So again, not great rectangles, but you get the idea, right? So, yep, we have 1, 2, 3, 4, 5, 6, 7, 8. No, okay, 9's not a nice number, but we have 9 rectangles, right? And so if I add up the areas of all 9 rectangles, you can see what happens. We get the area that looks very much like this red area in here. And so again, that gives us a pretty good approximation to the area. Now, why do I say approximation? because this is not exact, right? The exact area includes everything. So notice what's happening in here. This piece is not under one of the rectangles. This is not included, right? This little region in here looks like a triangle, right? But it's not exactly a triangle, because remember, this is a curve. It's a curvy thing up here. So they're little triangular regions, but they're really not exactly triangular, right? They're curves, right? And they're very small up here. There's not, you know. So I call these gaps, right? These little gaps in here. When you add them all up, you know, that might be pretty significant, and they're missing from the red area here, right? So when you add up the blue area here, these rectangles, you get an underestimate. It's going to be lower than the true area. It's going to be less than the red area in here, right? So again, it's not exact, but it's a pretty good approximation. And one way to get a better approximation is use more rectangles, right? When you use more rectangles, you get a finer and finer mesh, if you will, and that mesh will give you a much better approximation. If you watch the 3 blue 1 brown video, you've seen this in action, right? I can't animate this, of course, but that's Mr. Sanderson did a pretty good job of that. Grant Sanderson does those videos for 3 blue 1 brown, and I will I will give you the reference to that, the link on Blackboard, and you should take a look at that, because I can't do that justice here, right? He has wonderful computer graphics that can show you in much better detail than I ever could here. Okay, but in any event, right, the question is, right, so how do we find the exact area if we only have the approximate, right? So that's going to involve some sort of a limiting process, right? And before we can do that, we want to sort of, represent the little widths here, right? So I know we're starting at x equals 1 and 4, but let's do this more generally. Let's say we're starting at x equals a, and we're ending here at x equals b. Okay? And again, our specific curve was the square root of x here, but this could be any function, right? Right, any f of x, as long as it's, above the x-axis, right? As long as it's a non-negative function, let's say. Okay, because if it goes below the x, well, we'll talk about that later. If it goes below the x-axis, you get y values that are negative, so you might get a negative area, which we don't want. All right, so we know that the length of this whole thing here, going from a to b, we know that that's just the difference. That's just b minus a. And notice that we divided this into, well, in this case, 9 rectangles, but, 9 just happened to work out here. We can use as many rectangles as we want. Let's say we use n rectangles, right? So if we divide this up into n parts, right, then what's the width of each part, right? So we have to give this a name. We're going to call this delta x, right? It's a small change in x. What is the width, right? So the delta x is just the width of each rectangle. Each rectangle, right? Okay, it's this right here. That's the delta x, right? Well, right, if the total length is b minus a, and there's n of them, just divide by n, right? So delta x is just the total length divided into n parts. Make sense? Of course, we're assuming something here. We're assuming that all these widths here are the same, and they don't look the same. But let's suppose they are. That this is delta x, this is delta, right? So they're all delta x. So they're all the same widths, and that may or may not be the case. In some cases, you might want different widths for different rectangles. But let's keep it simple, right? It's much easier to keep all the widths the same. And in that case, we can use this formula to find the delta x, okay? All right. So that's the width of each rectangle. What about the height of each rectangle? Well, the height is going to be a little bit trickier, right? So let's look at this specific rectangle here. And again, right? So this is the rectangle we want. And we want to figure out the height, right? So notice the height is just the y value at this point, right? If I go way over here, oops, right, I have some y value, and I can calculate that by plugging in this right here, this particular x value. Let's call it xi, right? So if I plug in xi into this function, I get, well, you can say yi, right? I get the y value for this particular rectangle. Now, of course, different rectangles have different heights, right? So they're not all going to be the same. So that's why I have to use this I here to index which rectangle I'm talking about. In other words, which height am I talking about here, right? So they're all going to have different heights here. So, right, so what we're going to do is, right, so we're going to say f of xi, right, is the height of the ith rectangle. Right. So this one here is the fifth rectangle, so I is 5, right? The first one is I equals 1, and so on, right? But that's it. Now we can find the area of each rectangle, right? So now the area, let me do it this way. The area of the ith rectangle well, remember, it's the width times the height. Let's do the height times the width, right? So height times width. So what's the height going to be? Well, the height is right here. It's f of xi, right? F of xi. What's the width? Well, it's this delta x, right? So times delta x. And this is true of all the rectangles. Now notice the height will be different, even though the width will be the same for all of them, at least in this example. The heights will be different, right? So now, if I want the total area here, I have to add up all the rectangles, right? The areas of each rectangle. I have to add them all up. So if I want the total area of all the rectangles, think about what I have to do, right? I have to take the sum. So I'm going to take the sum, I going from 1 to n, because there's n rectangles, of f of xi times delta x. Now you see the power of this symbol, right? Because before, I would have to write this all out. I would have to write, you know, f of x1 times delta x plus f of x2 times delta x plus ... times, you know, f of xn delta x, and that's just clumsy, right? It's, you know, but that's what this means, right? That's what this symbol means here. So all of this is just a more concise, compact way to write all of that. Makes sense, right? And each of these terms, right? This is the area of the first rectangle. This is the area of the second rectangle. This is the area of the nth, the last rectangle, right? So yeah, I hope that helps. Okay, so that adds up all the rectangles, and we get the area of the rectangles. Now we don't get the area, the red area of the area under the curve. Remember, there's these little gaps here. Don't forget about the gaps, right? So we're not counting this, we're not counting that, we're not counting that, we're not counting that. And so remember, this will be the total area of the rectangles, but not of the entire curve, right? Of everything under the curve. Right. However, the more rectangles you use, the smaller the gaps, right? And as the gaps get smaller and smaller, you get a better and better approximation. Ultimately, you'll get, right? You'll get this. You'll get the exact area when you take the limit, right? So when you take the limit, and there's two ways of thinking about the limit here. One way is to say, well, you want more and more rectangles, right? So you want to take the limit as n gets bigger and bigger. N goes to infinity, right? At the same time, when you have more rectangles, each rectangle becomes thinner and thinner, right? You get very, very thin rectangles here, right? And so what happens is the width, this delta x, right? The delta x shrinks smaller and smaller. It goes to 0. So you can write it as the limit as delta x goes to 0, or the limit as n goes to infinity. And we're going to opt for, we're going to opt for the first one. N goes to infinity. Okay, so now if we want the exact area, let's say the area in red here, right, so that's this area up here on the top right. That exact area will be the following. It's going to be the limit, right, as n goes to infinity of the total area of all the rectangles, right? I goes from 1 to n. So we have n rectangles times f of xi. I'm going to change this to ci. You could use xi, but this works more generally. And then times delta x, right? So that gives us the exact area. Okay. So yeah, not an easy computation. And we're going to do one of these just to show you how sort of cumbersome, tedious, and awful this is. But we have to do at least one. You see it once, and then hopefully you never have to do it again. Okay. Okay, so this gives us the area. And I don't know if I should get ahead of myself a little bit here, but the symbol for this, there's going to be a symbol for this. This is going to be the definite integral from x equals a to x equals b of the function f of x times dx. Now this might remind you of the indefinite integral, but this is called a definite integral. So that's a D for definite integral. And what makes it definite is the fact that it's just a number, right? It's just a number. I don't know. It could be, 31.9. Okay, so that it's definite, right? It's a definite. It's an actual number, right? Well, if this limit exists, right? If this limit exists, then it's a finite number, right? But remember, whenever you take a limit, the limit might not exist. In which case we say this integral diverges, right, if the limit does not exist. Does not exist, right. And that could happen, but in most cases, and what we're going to do, that's not going to happen. So we're not going to worry about that. So in our cases, these definite integrals will converge, then you get an actual number. And what is that number? What does that number represent? Well, it represents the area, the red area up here under this curve. Right? So calculating definite integrals is really finding the area under a curve. Right. In a similar way that, remember when we talked about derivatives, derivatives were a way to calculate the slope of a tangent line. I'm not going to draw that now because we did that way back in chapter 2. But, so derivatives are slopes of tangent lines. Integrals are areas. They represent areas here. Okay. Okay, so, yeah, I think let's do an example so hopefully make this clear now. So I think this is our first actual example. This is all just the setup and the formulas, if you will. But we should be able to do an example here. So let's approximate the area under the curve. Let's make it f of x equals 9 minus x squared between 0 and 3. So between x equals 0 and x equals 3. And this is where I probably should draw the graph And as you know, it's very difficult to do on this pad here using this stylus, but I'll do the best I can. So let's say this is the y-axis. Let's say this is the x-axis, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that's the highest this is going to go. When x is 0, this is 9. And then we have 1, 2, 3, 4, but we're stopping at 3 here, right? So the graph of this function here is going to look a bit like this. So now I got to connect the dots. Oh, okay, it's a little wiggly here, but let me try that one more time. Actually, that might have been the best one I can do here, because this is going to be even worse. Okay. Anyways, right, you get the idea. We're going to find the area of this region here. But we're going to do it using just 3 rectangles. 3 rectangles. And the rectangles are going to look like this. So the first one will be this rectangle here. Let's see if I can... Oh, I need to turn this sideways, right, to get this right. Oh, that's not bad. Right, the second one will be this. And the third one will be this. Right. So you can see here that when I add up the areas, sort of the opposite thing happens here. I get a bigger area than I want, right? So the purple area is the area of the rectangles, but I want the area just under the curve, right? I want this green area in here, right? And some of it's the same as the purple area, but you can see that the purple area here goes over that, right? So there's extra area up here that should not be included, right? So this it's the opposite of what we had last time. It's the opposite of a gap, right? It's, I don't know what you call this, an overlay, right? So these are the overlays. This is the overestimate, right? So the area of the purple rectangle, the 3 purple rectangles, is going to be bigger than the area we want. Right. But let's do it anyway, right? Let's do it anyway, and let's see what we get here. Use purple. So there's only 3 rectangles, right? We can say this is n equals 1, n equals 2, n equals 3, right? And so what's the width of each of them? Well, we're going from 0 to 3, divided by 3. Our delta x, our width, is just 1, so that's convenient. So what's the height of each rectangle? Well, the height of the first one, right? So the height of the first is f of x 1, but x1 is 0. And f of 0 is 9 minus 0 squared, which is 9. Right? For the second rectangle, we're here. So this is x equals 1. That's my x2. So x2 is 1. So I get 9 minus 1 squared. 9 minus 1 is 8. And then for my last one, x3 is going to be 2. And so I get 9 minus 2 squared. 9 minus 4 is 5. So these are the heights of the 3 rectangles. Now we just multiply by the widths, right? So we get the area is the sum. Oh, I shouldn't use this color. I'm sorry. Let me go back to something a little more usual here. There we go, right? So the area is going to be the sum, I going from 1 to 3, because there's only 3 rectangles, all right, of f of x I delta x. But writing out them term by term, right, there's only 3 of these, right? So it's f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, which in this case, right, f of x1 is just 9, and delta x is 1. F of x2 is 8, and delta x is still 1. And f of x3 is 5, and delta x is still 1. So we just get 9 plus 8 plus 5. So that's 17 plus 5, 22. So that's the approximate area. That's the area of the purple rectangles, which of course is more than the green area, right? So this is way bigger than the exact area. So it's approximate. In fact, it's not even a very good approximation. You can see that there's way too much area here for the purple rectangles that should not be included under the curve, the green area that we wanted. Okay, so a very bad approximation, but you know, look, if you want a better approximation, we should have used maybe 6 rectangles or 10 rectangles or 100, and we would have gotten a much better approximation. The drawback to using more rectangles is, right here we only had to add up 3 numbers. If you use 100 rectangles, you have to add up 100 numbers. So that's much more tedious, right? And if you want the exact area, well, then you have to take a limit, right? As n goes to infinity. Once you take that limit, then you get the exact area, right? And so that's going to be next. We're gonna do that. Before we do that, just some sort of technical details that we have to get into. This is going to be theorem 4.3. Actually, let me bring it up. Give me a second. Okay, here it is. Theorem 4.3, so I don't have to write it all out because this could take a while, right? So we have something called the limits, the lower limits and the upper limits, the lower sums and the upper sums, right? So we have a continuous function, right? Continuous function and non-negative, so it's above the x-axis, right? Between a and b. So think of that as the domain, at least for now. The limits of the upper and lower sums, right? So this is the first one here, right? When you have f of mi, that's the minimum value on the given interval, and then the capital Mi, that value, when you plug it into the function, you get the maximum value on a given interval, right? And so whether you take the sums from the lower values, the lower sum, which is this limit here, or the upper sum, which is this limit here, you get the same thing, right? Once you take the limit, it doesn't matter which one you choose. So I know that might not be clear. Let me try to draw it out and show you what I mean, right? So we have our function here. Let me do better than that. Okay, so I'm just going to draw some generic function, right? That's my f of x, if you like. And we're going to, instead of drawing all the rectangles here, I'm just going to draw one. Let's suppose this is my delta x, and I know it's very wide, but you know, you can make it smaller, but then it's more difficult to see here. So I'm going to try to go straight up here. Oh, that's not too bad. Try to go straight up here. Oh, that's a little sloppy. All right, close enough, right? So this is my delta x, right? This could be one of the rectangles, right? Okay. So what would the mi be? The mi would give me the minimum height of the rectangle. That would be right here, right? So that happens here. This would be my mi, lowercase mi, right? Right. So that's the smallest area this could possibly be. The biggest area would be way up here, right? It would be this whole rectangle. Oh, sorry. Very difficult to draw a vertical rectangle here. Let me try one more time. All right, close enough, right? So that's this area in here. So this would be my capital Mi, and that would be the maximum value on that interval, right? And yes, they happen to be at the left and right endpoints, but they don't have to be, right? Obviously, if your width is over here, then the minimum would be right here in the middle, right? That would be the smallest rectangle, and the maximum might be over here somewhere. So it depends, right? So if you didn't follow that, honestly, I wouldn't worry too much about it, right? We're getting into the technical definition of what's called the Riemann sum, and for that, I really don't think you have to worry about it. It's not going to come up, right? It's not going to come up on a test, obviously. Okay. And this definition here, I think is one we already did. You have a continuous non-negative function, like this function here, and the area of the region bounded between x equals a and x equals b. So let me see if I can draw that over here again. Right, so that's going to look like this. Right, so here's my function f, and we want the area between, let's say, oops, nope, different color. So this is my a here, and let's say way over here is my b. And so I want to calculate this area exactly, right? No rectangles. I want the exact area of this entire region. Okay. So that area is given by this limit here. Right, so the area is given by this limit here. Right, and I did something similar. The difference is instead of using xi, you can use either xi minus 1 or xi, that's the left-hand endpoint or the right-hand endpoint, or any point in the middle. Right, and generally speaking, we're either going to use the left or right-hand endpoint. If you want to use the middle, that's fine, or if anywhere in between, right, xi minus 1 and xi, that's fine too. Okay. Again, these are technicalities. We're not going to worry too much about that going forward. Okay, now we get to finding the exact area. Find the exact area under the curve, and we're going to do the same example, 9 minus x squared. Right? So our function, if you can't see it, let me write it down again. F of x, right, is just 9 minus x squared. And we're going between 0 and 3, right? So that's my interval. In other words, a is 0, right, and b is 3. Okay, right, and we're going to use the definition that I just erased, but I will remind you that the area is going to be the limit as n goes to infinity of the sum I goes from 1 to n. Right, so it's not just 3 rectangles anymore. It could be 6 rectangles, could be 100, could be 1,000. Right, we want to make them bigger and bigger. Right, of f of ci times delta x. Right, where if you remember, the delta x, right, is just b minus a over n. Right, or in this case, 3 minus 0 over n. Right, so that's just 3 over n. Right, so already we can simplify this a little bit. We can take the limit as n goes to infinity, the sum, I going from 1 to n, I hope that's not too small, of f of ci times 3 over n, because that's what delta x is, right? So that's 3 over n. All right, now the hard part is figuring out the ci's. Okay, so I'm going to go through this slowly here. So this is my interval. We're starting at 0, we're ending at 3, and we're dividing this into n segments, right? 1, 2, 3, 4, 5 and a half. Okay, so pretend these are all uniform here, right? So what do we want to use for our CI? And I guess the question is, do we want to use the left-hand endpoint or the right-hand endpoint? So if we, oops, hang on. If we use the left-hand endpoint, well, okay, so if we use, let's start with the right-hand endpoint, right? In other words, we're starting, right, x1 is here, x2 is here, x3 is here, and then this will be xn, right? So for the right endpoints, right, my CI is just going to be, sorry, that looks like CC. I know my eyes have a little bit of a tail here, right? So CI, this is just going to be A plus I times delta x. Okay. So that's for the right-hand endpoints, right? If you want the left-hand endpoints, then your CI is going to be A plus I minus 1 times delta x. So yeah, it's not that bad to deal with the I minus 1, but it just means, right, you're starting here for your x1, x2, and so on. And of course you could start in the middle too, but let's not do that. Let's keep it as simple as possible. So I'm going to opt to use the right-hand endpoints here, right? All right. So yeah, so we have to calculate this these CIs here. So what's our A? Remember, way back up here we said A is 0, so that's nice, right? So this is CI equals 0 plus I. Well, we don't know what I is. I is just the ith rectangle. It's which one we're talking about, right? It could be 0, 1, 2, 3, 4, 5, and so on, right? And delta x. Well, we know what delta x is, right? It's this 3 over n. So times 3 over n, right? So this is really just 3i over n. That's my CI, right? So now we can do this a little bit better. We can, remember, we got to keep writing limit. That comes at the very end. And we got to keep writing the sum too. So that we keep writing. And now we know what the CIs are. This is f, right? And we're plugging in these particular values of x, right? These are just x's. These are just different x's. So 3i over n times the 3 over n, that's the delta x, right? Remember, that came from here. Okay? Okay. So now what? So what is f of x? F of x, well, that was given. That was 9 minus x squared, right? That's the curve we're looking at here, right? So what's my x? It's this 3i over n. So I have to just replace this x up here, right, with 3i over n. Right? So that's going to be, let's see, 9 minus x, which is 3i over n, squared. Right? So that's my f of 3i over n. And all of that gets multiplied by 3 over n. Okay, so far? So hang on, because this is not going to be easy, but like I say, I'm going to try to go through it step by step. So I'm taking a little bit of a pause here to make sure you followed each little step here. All I did was replace the x with what's in the parentheses, the 3i over n. All right, now we can multiply this out a little bit here. I know it's a pain to write limits and the sum, but we're not done with them yet, so we got to keep going, right? This is an I. All right, so what's in the bracket here? We have 9 minus 3 squared is 9, I squared over n squared. So I just distributed the 2 here. We still have 3 over n. So just doing a little bit of algebra here. Right. And I'm trying not to skip too many steps here. So what do we do now? We distribute the 3 over n. So 9 times 3 over n is 27 over n, minus 9 times 3 is also 27, but this is I squared, right, over n times n squared, which is n cubed. Okay? So now this is the thing we're adding up, right? So how do we add all these things up? Well, first of all, remember that we're adding up the difference, and just like in the previous video, you can split them up and add them up separately, right? In other words, we're going to do the sum, I going from 1 to n, of 27 over n, minus the sum, oops, make that a little bit better here, the sum, I going from 1 to n, of 27 over n cubed times I squared. Okay, and we still have to take the limit of all that. Okay, let's keep going. So we still have to take the limits. So what is this? Now notice, you might think n is a variable here, but remember, n is just the number of rectangles, right? I is the variable, so this doesn't depend on I, right? This 27 over n, there's no I here. So it's a number, it's a constant, right? And that constant can come outside the sum. Right? So what are we adding? Well, we're just adding 1s now, right? And if we're going from 1 to n, 1 plus 1 plus 1 plus 1 plus 1, right? N times is just n. So this is going to be the limit, n goes to infinity, of 27 over n, and then all of this here is just n. So multiplied by n over 1. So n divided by n is 1, so they cancel, right? So this first term here is just 27. Oops, limit n to infinity, 27, right? Now we got to look at all this over here. So what are we subtracting here, right? So in this term here, this term here, what's the constant here is this 27 over n cubed. That can come outside. That can come outside of the sum. Now what are we adding up? We're adding up I goes from 1 to n of I squared. That should look a little bit familiar. If it doesn't, I guess I'll have to remind you. But you can look it up, right? It's a formula. I goes from 1 to n of I squared is just n times n plus 1 times 2n plus 1, right, plus 1, all over 6. So that's all this, right? I'm just going to replace all that with this mess up here, plug that in here, and what do we get, right? So we get minus, we still have the 27 over n cubed, and now we multiply by n times n plus 1 times 2n plus 1 all over 6. Yep, so again, we needed this formula from the summation video, the last video. It's still 4.2, but it was in the first part of this, right, where we talked about this. And again, if you forgot, you can look over that video, or you can look in the book. The formula is given. You don't have to remember the formula, right? You can always look it up, right? Okay, now we get this big mess here, and this is a lot of algebra. And because I really want to make this next step as simple as possible here, right? We're just subtracting this. I'm going to do this one separately over here. So what do we have? We have 27 over 6, right? 27 over 6. We can reduce that. Let's multiply this out, right? We're going to get n squared plus n times 2n plus 1. So if you multiply all that out, you're going to get 2n to the third power, right? Then you're going to get 3n squared plus 3n squared, and then you're going to get plus n. Again, don't believe me, multiply it out, right? You just got to either FOIL it and then multiply by n. I think that's how I did. I did 2n squared times n, 2n cubed, and then n plus 2n is 3n, and then times n is n squared, and then 1 times 1 is 1 times n, so that's the n there, right? And then we're dividing all that by n cubed times 6. I put the 6 in front, right? So what's this 27 over 6? That reduces to 9 over 2. And all of this, if you divide by, right, 2n cubed divided by n cubed, plus 3n squared divided by n cubed, plus n divided by n cubed, we can simplify that. Oops, sorry, that's a 9, not a 7. So 9 over 2 times, well, you cancel both the n cubes here, you just get 2, plus, this is going to be 3 over n, plus 1 over n squared. Okay. And we can distribute the 9 over 2 here. So this is going to be, well, 18 over 2 is 9, plus, this is 27 over 2n, plus 9 over 2n squared. So a lot of algebra, but that's what this thing up here equals. Okay, so we're subtracting the whole thing, so we need a bracket around it, right? We're subtracting 9 and a 27 over 2n, and the 9 over, that's a plus, 9 over 2n squared, right? Close bracket. so now we're almost done, right? We still have to take the limit, but notice that in the previous two steps, I got rid of the sum because I added them, right? I took the sum. So this is the total sum. Now we can take the limit as n goes to infinity. And we'll distribute the negative here, right? This is going to be 27 minus 9 minus 27 over 2n, and then minus 9 over 2n squared. Okay, so, oops, sorry. What do we do now? Well, 27 minus 9, I think that's just 18. Yeah. Minus 27 over 2n minus 9 over 2n squared. Now we just take this limit. Okay. And if you remember way back in 3.5, section 3.5, we talked about how do you take the limit of something like x goes to infinity of, how about, 3 over x to the 4 or something like that. So it doesn't matter what the numerator is. If the denominator gets bigger and bigger and bigger, right? Think about 3 over a very big number, like 1 billion or something. Right? It's going to be a very small number, 0.000000003 or something, right? So, right, and as x gets bigger and bigger, the whole fraction gets smaller and smaller. It goes to 0. Okay. So using the rules for limits now, this is the limit as n goes to infinity of 18 minus, and you can take the number, the 27 over 2 out. This is the limit as n goes to infinity of 1 over n, and then minus the 9 over 2 times the limit as n goes to infinity of, 1 over n squared. So yes, we're using n's instead of x's, but, change them to n's. It's the same thing, right? This fraction here, as n gets bigger, the fraction gets smaller, right? 1 divided by a big number is a small number, right? So this fraction here, this goes to 0. This fraction here also goes to 0. And now, when you take the limit of 18, you get 18 minus 27 over 2 times 0 minus 9 over 2 times 0. So 18 minus 0 minus 0 is a grand total of 18. Okay, so I know this was very tedious, and you can see what a hassle this was, a very lengthy, tedious calculation. But in the end, we got our answer, right? The total area, right, when we calculated this mess here, that area turned out to be just 18. Right. Remember earlier we did the approximate, well, we only did 3 rectangles, right? Remember the area for the 3 rectangles. We got an area of 22. And remember we said that that's way too big, that we had an overlay of areas that should not be counted. And now we can see that, yes, that was way too big. It's actually less than that. It's exactly 18. Okay? And so, yeah, so very tedious, very lengthy calculation, but we get an answer of 18. So here's how I would think of this, right? Remember way back in chapter 2 when we talked about the derivative, right? When we defined the derivative, right, f prime of x, we calculated the derivative by taking the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. And yeah, remember, this was kind of a pain, right? This was a lot of algebra. This was maybe, 5 or 6 or 10 steps, depending on how complicated f is, to be able to get the derivative this way, right? Using the definition is a very tedious, cumbersome process. It's not very pleasant. And in the end, you take the limit and you get the derivative, right? On the other hand, you know that when we have something like, again, that's not equals here, 5x to the 8, and you want the derivative, there's no way you're going to use the definition anymore, right? We haven't done that for months, right? We did that maybe in the first 3 or 4 weeks of class. After that, I think I told you, yeah, never do this again, right? You're not going to use the definition to take the derivative as a practical matter, right? You're going to use the rules, right? You're going to use the power rule. 5 times 8 times x to the 8 minus 1, which is 7. So 40x to the 7. And what could have taken a long time using the definition, probably a very long time, was so much simpler, right? Using the power rule for derivatives. So what does that have to do with this? Well, this is the reverse process, right? This is not derivatives anymore. This is an integral, right? What we took here was the integral from 0 to 3 of the function 9 minus x squared with respect to x. That represents the area underneath the curve. And the answer, well, as this really horrendous process shows you, that answer is just 18. Okay? Remember, definite integrals are numbers. There's no plus c here, right? Those are indefinite integrals. These are definite integrals. So when you see these numbers here, right, this 0 is referred to as the lower limit of the integral. And this 3 here, if I can squeeze that in here, this is the upper limit. Right? And it really refers to, when you look at the graph, it refers to the different color here, the left-hand endpoint over here, and then the right-hand endpoint over here. So the lower limit's really the left boundary point, and the upper limit is the right-hand boundary point. Okay? And just to remind you, right, what this area is, right, remember the graph looked like this, and so it's this area in here. So that's the 18, right? This is the 3, the 0, and then the curve here is, of course, just y equals 9 minus x squared. So we found the exact area under the curve using this process here. Now, yeah, so of course, you're probably not going to have to do this, maybe just once, right? You do it once for the homework, and you never do it again, right? Just like with the derivatives, you don't take the derivative by using the definition. This is the definition of the definite integral here, right? This thing here is taken as the definition. And so, of course, it's going to be a very long, tedious process to get to use the definition. Right. So in maybe the next couple of videos, later on, I'll show you a shortcut to this. Right? I shouldn't say shortcut. It's basically a formula, right? It's a formula that you can use to calculate this 18 without having to do all this, right? In the same way that, once you know the rules for derivatives, right, you can use those rules to take derivatives without having to use the definition. So likewise, there are going to be rules for how to calculate these definite integrals without having to go through this process. And personally, I don't blame you if you don't want to do this ever again. In fact, you don't have to do this in the homework if you don't want to, right? Because it's just a few more videos away, and I'll show you a much better process to this, right? And the reason for going through this is, well, you have to know what an integral is, right? You have to know what the definite integral means. Just like when we talked about derivatives, you have to know the definition. You have to know what it means, right? As a limit, as a process, in order to understand that, oh yeah, I'm just going to use the rules, but I understand that this is a limit, and it's, the instantaneous velocity or the slope of the tangent line, right? So likewise, when you see these definite integrals, they're just areas, right? They just represent the area, and this is the formal way to calculate it. But again, it's very tedious. And so, yeah, so I would say you simply don't have to do this this type of thing anymore, because when we learn the shortcut, you're going to see that there's no reason to go through this. But I did want to show you once, and once is enough. Once is enough for this and for anything this horrible here. So if you didn't follow any of this, don't worry about it. You're in luck because this will not be on the test, right? So I'm never going to ask you anything like this.